So now, since a phasor, we have studied that a phasor is a complex number in a polar form, that means that we can also convert this polar form into other, convert the or express the phasors in terms of other uh, complex number forms. So we can have a rectangular form and we can also have exponential form. Now, the idea why do we want to study or changing the forms of the phasors is simply because in some mathematical operations, like for example the plus, minus, the multiplication, and the divide, in some or in addition and subtraction, the rectangular form is actually more convenient to work with. And in terms of multiplication and division, then the polar form is more convenient to work with. So that is why we need to study how to convert the polar form to rectangular form, or vice versa. Okay, another one, there is also exponential form, but we'll just focus on these two forms at the moment. So right here we have a rectangular coordinate systems, and since it's a complex number, then that means we are in a complex plane. That means that the horizontal axis is the real number and the vertical axis is the imaginary number. And if this is our, let's say, if this is our point right here, our point, or the length of this phasor, maybe not a point, we will just write a phasor. Here's our phasor, and that length of phasor um, is expressed mathematically as x plus jy. So what that means is we have some value of this x. So for now, I just write x, but actually that's the real number, and then the y corresponds to the imaginary number. So any value of x here, let's say we have this x-axis and y-axis. Just 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 keep in mind that this x-axis or the x value is or refers to the real numbers, then the y values refers to the imaginary numbers. So here's our x, and we also have our y right here. Right. Now, in terms of polar coordinates, here's our phasor again. So the length of this is the radius, and the angle. It is described by the radius and the angle because it is polar. The representation of this would be z is just simply equal to r angle theta. We already learned this, and for the rectangular coordinate we have z is equal to x plus jy. That's the rectangular coordinate representation for the phasor. Okay, so how do we convert this from one point to another, from one coordinate to another? So let's superimpose. That means that we have the uh, x and y here, and we also put the polar coordinates here. And what we can see is actually a right triangle. And whenever we have a right triangle, then we can apply the Pythagorean theorem as well as the trigonometric identities to find the values of what we are looking for. So let's say we're given let's say we are given the r and cosine, r and theta. So how do we convert, let's say, from polar to rectangular? So we're given r and theta, so let's convert these to x, of course x and y, right? So x, y. So how do we convert that? So of course, if we are given r and theta, that means that we have the values of r and we have this theta value. So to convert that to x and y, right, theta, and I'll just write the rectangular in terms of this red color. We have the y and we have this x. So what's the relationship of x in terms of r and theta? So x is just simply the cosine of theta, cosine of theta. Or let's write cosine of theta is just simply x over r, right? Or you can write x is equal to r cosine of theta. Now for y, how do we find y? That is sine, right? Sine theta, that's the opposite of our hypotenuse. Sine theta is equal to y all over r. The r is the hypotenuse, and therefore y, we can write y as r sine theta, right? And therefore, it's going to be z is equal to the, or the magnitude of this is just equal to a square root of course, the hypotenuse, that's the x squared. Sorry, I think that's just all. Maybe we'll just write, sorry, z is just equal to x, whatever the value of x here, plus jy. So that's the rectangular representation expression of a phasor. Okay, so that's one way. The next one is, what if we are given a rectangular and we are going to change this to polar? Okay, so if we are given a rectangular, that means we have the value of x and y. So x and y, and we need to find, let's put this, let's make this red. So x and y, and we are to find, maybe we'll change this to blue. And this one is red. Okay, and then we are going to find the r and the theta. So how do we find that? Then let's draw again our right triangle. So here's our x, and here's our y. So x, and this is y, and this will be our phasor. And how do you find r? How do you find r and this theta? So by trigonometric relationship, we can find this r and theta. R is just simply the hypotenuse, which is just x squared plus y squared square root. Then the theta is, recall that tangent theta is equal to the opposite divided by the adjacent, y over x, or theta, or the angle phi, is equal to the inverse tangent of y over x. Right, so these are the conversion. Therefore, since we now have the r and the theta, then we can write the z is equal to r angle theta. Phi. So that's how we convert one to the other, polar to rectangular, rectangular to polar. Okay, so as I've said that we need to convert the forms because sometimes in some operations like multiplication and divisions, it's more convenient to work with polar forms, and for addition and subtraction, it's more convenient to work with rectangular forms. Okay, so to review some basic operations, let's say addition and subtraction. When we have two complex numbers, we have z1 and z2. So we have complex numbers, z1 and z2. So when we do the computations or the addition, that means that we just add the real numbers together, x1 plus x2, and then plus j, and then add the imaginary numbers. So the same is true for subtraction. If we want to subtract a complex number, then that means we subtract all the real numbers, and then we subtract all the imaginary numbers. Notice that we are in a rectangular form. For multiplication, this is in polar form, multiplication and division. And so z1 times z2. So what that means is we just have to multiply the radius or the magnitude of the two complex numbers. And then in terms of the angles, we just have to add the angles. Of course, algebraic sum of the angles. That means that we need to take into account if it's negative or if it is positive. For division, z1 divided by z2, this just simply means we divide the magnitude r1 divided by r2. Then the angles we just need to subtract. Okay, so let's do some computations. So sample problem 4.3, another reference that we have. We're asked to convert a rectangular to polar, given in polar form, and we need to convert it to rectangular. Then another one given in terms initially in rectangular, and we are to convert this to polar form. Okay, so to do that, then maybe we can just write it here. So for number 1, then polar, we'll write here polar. So polar to rectangular. What's given to us here is the r is equal to 5, and then the angle is equal to 30 degrees. So if you want to convert this to rectangular, we just need the x and the y values. So the x value is r cosine theta, or phi, and then we substitute the r5 cosine 30, and that is 5 cosine 30, that is 4.33. So 4.33 units. And then for y, this is r sine theta, or phi, that is 5 sine 30. So we input this into the calculator, 5 times sine 30, and this is 2.5. So 2.5. Therefore, our z in terms of rectangular forms is x plus jy. Our x is 4.33. 4.33, okay, plus, because this is positive, plus j, 2.5. Okay, so there we go. The next one is convert to polar. So rectangular is given, and we need to convert this to polar. So rectangular, we have the x and the y. So x is, what is x? 10. Y is 5. So for polar, we need the r value and the angular value. So r is just simply equal to square root of x squared plus y squared. So 10 squared plus 5 squared, square root, and that is 100 plus, I think this is 100. 10 squared is 100 plus 25, and we take the square root of this. What we get is 11.18. 11.18. Okay, next one is the theta. So the theta is the inverse tangent of y all over x, which is 5 all over 10. This is a shift tangent of 5 all over 10. This is 26.56. This is 26.56 positive value. That means if we need to draw this, we have a value of 11.18, and the angle right here is 26.56. Now for this one, the x value is 4.3, and then the y value, xy, then we have here. So here's our z is equal to 4.33 plus j. 2.5. Okay, so last sample problem we have is we need to do the operation. We are given two complex numbers, z1 and z2. z1 is 5 plus j5, and then z2 is 3 minus j4. And we are asked to find the sum. We are asked to find the the difference and the product and also the quotient. So let's do that. And recall also that addition and subtraction, we need the rectangular form, and multiplication and division, we need um, polar form. So I think let's do the conversion first. So convert. Right, so number one, say convert to, or maybe write, not convert, maybe write the polar form of the given complex numbers. So write the polar form of the given complex numbers. Okay, so z1 in terms of polar, so z1 is equal to, what is r? So r is just simply square root of x squared plus y squared. So 5 squared plus y squared, so 5 squared, right, times the inverse tangent negative 1 of y all over x, so 5 all over 5. So 25 plus 25, square root of 50. We have square root of 50. This is 7.07, and the inverse tangent of 5 over 5, I think this is just 45. Alright, so 45. So angle 45 degrees. Okay, next for z2, this is 3 minus 4. That's just simply 3, 4, 5. That's a 3, 4, 5 triangle. 3 squared plus 4 squared times the tangent of, inverse tangent of 4. Take note, negative 4 all over 3. What we get is, this is 5. That's a 3, 4, 5 triangle, and then so shift tangent of negative 4 all over 3. Okay, that equal to negative 53. So angle negative, that is negative 53. Okay, next is, let's do the operation. Okay, so z1 plus z2. For letter A, z1 plus z2, that means that z1 is 5 plus j5 plus 3 minus j4. So we add the real numbers together. 5 plus 3, that's 8. Okay, plus 5 plus negative 4. That is just j1, or we'll just write j. Okay, next one is letter B. This is 5 plus j5, and then minus 3 minus j4. So we add the real numbers, or we subtract the real numbers together. 5 minus 3, that is 2, and then 5 minus negative 4, and that will be j9. Okay, next one is letter C. Multiplication, so z1 times z2, and we will use the polar form. We have z1 times z2. z1 is 7.07, angle 45 degrees, and z2 is 5, angle negative 53 degrees. Okay, so we multiply this. 7.07 times 5. This is equal to 35.35. Then the angle, we add the angle together, 45 minus 53. And what we get is, I think negative 8. It's a negative 8. Then for letter C, Z1 divided by Z2, so 7.07 angle 45 divided by 5 angle negative 53. Okay, 7.07 divided by 5. This is 1.44. 1.414. Okay, 45 minus 53. Sorry, 45 minus negative 53. This is 98. So angle 98. Right, so that's our value for our product, the sum and the difference, and as well as the quotient. Okay, so again, just to have a summary of what we discussed so far in this week topics, we first discussed the significance of these AC systems, and then we dealt with the sinusoids. We talk about the sinusoids, the mathematical expressions, the anatomy of the waveform, and then we talk about the phasors. So instead of expressing or doing the computations in terms of sines and cosines, we convert this into something like a rotating vector. That's what we call phasor. And the phasor is mathematically expressed as a complex numbers. So that is why we studied the conversion of since it's a complex number, so it is also necessary to be able to transform the polar form to rectangular form or vice versa. Just simply because the mathematical operations, they are more convenient to, let's say, the plus and minus. It's more convenient to rectangular, and the times and the divide, that's convenient for polar form. Okay, and we just reviewed this basic complex operations. So just take note of this basic, because there's still many other operations. That's maybe also basic, but we just excluded it here. Okay, so in the next video we will be dealing with single phase AC systems. So see you in the next lecture.